Okay, so we go back to class, and the slide just shows some important information. As I mentioned, you don't need to remember the certain values for the viscosity or density, because for the example or exercise, I will provide the number for you. Okay, so these questions, the one question showing here, the tank have the gas and the gas flow out. And because the flow out, so will provide the moving force. So the car will move to the left. But the key knowledge for these questions is what about the densities for the air? So the property, if you would like to have the density numbers, you need to keep in mind, first you need to double check the temperatures and the pressures, and then you have the table. You can check out what's the density of the air under these conditions. Okay, so as the words showing here, usually you don't need to remember the value, but you need to understand where the table you can find out the solutions. Okay, so for our case, I already upload the table appendix 3 on E3 website, so you can download by yourself. Okay, so this slide just introduce the specific gravities, and usually the equations are shown here. So you just look for your gamma and the density for your material, and divided the density of the water and divided the gamma of the water at the 4 degree. And sometimes the SG numbers can help us to figure out the material will flow or sink on the water, because the density is relative to the water. So as I mentioned, summarize the sentence here, the SG smaller than 1, that means the material will float on waters. But the SG larger than 1, so it generally sink. Okay? But for different material, actually have the different SG numbers. I just quick list some important material like the seawater, mercury, steel, aluminum, and concrete. Okay, but you can see some material has some different property. We call that the miscible and the immiscibles. That's the oils and the alcohol. Okay, even though the SG is smaller than 1, and then we may say that will float on the waters, but some material will mix together, so not float. Okay, will mix together. Okay, so this is just a very simple exercise. We take a look at the question first. The specific weight for the mercury gamma is 133 kilonewton per cubic meters. And please calculate the density and the specific gravity. Use the SI units. Okay, so we already have the gamma. Okay, so the gamma is equal to 133 kilo Newton per cubic meter. Okay, and then we know that the gamma is equal to the rho G. So the rho for the mercury is the gamma divided the G. So first one is very easy. You just have the 133,000 Newton per cubic meter divided the gravity constant 9.81 and the meter per second square. And then you have the density. So you can compute it by yourself. So the density is around the 13557.6. and it's kg and per meter cubic. Okay, so this is our first answers. And then the second question is the SG. Because we already have the law, and we simply can compute the SG value by the ratio between the law and the law W. The law W is the waters. And as we know, the water's density at the 4 degree is around the 1,000. Okay, so the specific gravity for the mercury is around the 16.6. Okay, so the exercise is quite easy, but I would like to just figure out and would like to you practice how to compute the SG numbers. And you can have this SG number is quite larger than 1. That means the mercury may sink on the water. Okay, so this is very simple. So I just quick do the exercise. So the most important ideas, usually we say that for the liquid and in the steady flow, that means the flow property didn't change with the time. So we call that the steady, right? As I mentioned before, the steady state means the physical property didn't change with the time. Okay, and then are assumed to have the constant density. And we call that it is the incompressible flow. Incompressible flow. But there are some notable exceptions. Will be talked about the idea on the chapter 12. Okay, so that means some liquid under some conditions, the material can be compressed. But for the normal liquid, it's incompressible flow. OK， 大部分的 liquid 都是不可压缩流，但是实际上有一些例外。但这个例外我们会在 Chapter 12才会讲到，可是我们这个学期只会上到 Chapter 大概 9或者 8这样子，所以大家要有一个印象，其实有些条件下是有可能可以压缩的。Okay, and then for the gas, so the bottom for the gas also in steady flow, but the density can be assumed to be constant if the Maher number is less than 0.3. So what is the Maher numbers? I have provided a certain definition. The Maher number gives a ratio between the fluid speed to the sound speed. Okay, so as I mentioned, the gas can be changed, right? The density of the gas can be changed because the gas can be compressed and the volume will be changed and density changed also. But under this condition, the gas cannot be changed, the volumes. So will be satisfied the incompressible flow. Okay, the special case for the gas. But for the liquid, always, we can say always not. It is the incompressible flow for the liquid. But for the gas, this is a special case. Under this condition, we can say the gas is incompressible flow. Okay? So this is also the topic related to the density. And we introduce the bulk modulus and the equation define the bulk modulus. The delta P, what is the delta P? If we have the before, this is the before pressures. And before pressure, we call that is the P1. And after pressures, we say that is the P2. So the delta P is the after pressure minus the before pressures. So what are the after and the before? we call that this is the process related to the compress process. So the P2 always larger than P1 because we do the compress first. So under this condition, the delta P always positive because the P2 larger than P1. We do the compression experiment. And what the delta V? The delta V here, we said there is a delta V. So the delta V, we have the before volume, we call that the V1, and after the volume, we call it V2. So we also can compute the delta V is the V2 minus V1. As I mentioned, the P2 larger than P1, right? So we do the compressions. So that means maybe the V2 is less than V1, right? If you compute the delta V should be the negative values. So that's why there is a minus here. Because the bulk module is always positive. The bulk module is always the positive. The positive and the delta P also positive, but the delta V is negative. So we need additional minus to be the positive bulk modulus. Okay, so the physical meaning for the minus here, because you do the compression first, and then the volume will become smaller. So you need to additional minus to balance the delta V negatives. Okay, so what are the V? V is the initial volumes. So here the V is the initial volumes. So the V is equal to V1. Okay, initial volumes. Okay, so that's why I say if the bulk modulus is larger, so my question is bulk modulus is larger, that means the delta P is larger, and then delta V is smaller, right? And then bulk modulus will become larger. So that's why I emphasize the bulk modulus larger. That indicates the material difficult to deformations. Even though you have a very larger delta P, but the delta V change is quite smaller. That means the material difficult to compressions. Okay, so that's why usually we say that is incompressible, okay, because the bulk module is larger and then the material is incompressible. Okay, so but for the gas, for ideal gas, the bulk modulus will equal to environment pressures. So this is under the isothermal process. Please prove why the EV is equal to P. Environmental pressure is equal to the P2, right? Because after we do the compression, so the environmental pressures is P2. So that means under the isothermal process and the ideal gas law, the EV will equal to P2. So please prove this relationship. So based on the IGL, we know that the P1 V1 is equal to nRT1, right? And the gas is constant, didn't change, right, during the process. And then the mole number also just the same on the same tank. Okay, so no more cannot be changed between different processes. And the P2 V2 is equal to nRT2. And based on the isothermal process, That indicate the T1 is equal to T2 is equal to T, right? They are the same. So we can rewrite the equation is the P1 and the V1 and the nRT and the P2 V2 and the nRT. Okay, and then we can reorganize the equation so the P1 is equal to nRT divided the V1 and the P2 is equal to nRT divided the P2, and then we compute the delta P is equal to P2 minus P1, and the same parameter I just take outside, nRT are the same for the P1, P2, and so the inside only have the V1 minus V2 minus V1 over 1, right? And then we can nRT keep it, and it will be equal to the V1 V2 and the V1 minus V2, right? It's V1 minus V2. Okay, so we can keep the V1 inside and take the V2 outside. So we can rewrite this as nRT and the V2, and the inside is the V1 over then V1 minus V2. And the V1 minus V2 is minus delta V, right? V1 minus V2 is nRT and divide V2, and the inside is minus delta V divided the V1. Okay, so we can summarize, reorganize some important things. So I move the delta P and here the minus delta V and divided the V1 is equal to nRT divided the V2. And the nRT divided the V2 is equal to the P2, right? And the left hand side here is just our bulk modulus. So we proved finally under the isothermal process for the ideal gas, the bulk modulus for the gas will equal to environment pressures P2. Okay, this is a very good concept. If your gas satisfies the ideal gas law, and then your environment condition is under isothermal, and then you don't need to check the table to find out the bulk modulus, because the bulk modulus is equal to environment pressures. Okay. Oh, and then as I mentioned, another process we call that the adiabatic process. That means the heat energy didn't change along the interface. Okay, in that way, the bulk modulus will equal to the K multiplied the environment pressures. What the K is the adiabatic exponent I have introduced before on the previous slide. Okay, so most important two equations is EV equal to P and the EV equal to KP, but under a different process. Okay, so we just practice. The previous slide focused on the gas, and I tell you for the liquid didn't be changed the volume, right? The volume didn't be changed. Okay, so you see the question is for the waters. So we have liquid waters, and what are the volumes of the water? The volumes of the water is equal to 1 liter. And 1 liter is equal to 10 minus cubic meters. And the question tells you this question is based on the isothermal compressions from the atmosphere pressures to a pressure of the 1 million absolute pressures. Okay, so that means our P1 is 1 atm, right? And the 1 atm is equal to 101.3 kilopar. And the P2 is 1 million par. Okay, so this is our V1. And the question is, what is the change in the volumes of the waters? So, what is the answer? Can we say that the bulk modulus is equal to environment pressure? We can't, because this relationship only for the ideal gas. But right now the material is the water, right? So we need to compute by ourselves. We did not satisfy this relationship. This relationship only for the ideal gas. So I tell you the water, the bulk modulus for the water, EV is equal to 2.2 giga, the 9 powers newtons per meter square. And based on the certain definition of the bulk modulus, we actually know the EV is equal to delta P minus divided the delta V and then multiply the V1, right? So what is the delta P? So this is our equation 1. So we can compute the delta P first. The delta P is P2 minus P1. And the P2 is 1 million par minus the 101.3 kilopar. So you can compute the answer first. So we have 1 million par minus the 101.3 multiplied 1000. So the pressure difference is the 898,700 par. Okay, and we didn't know the delta V because the delta V is the answer for these questions. What is the change? What is the change in the volume of the water? So the delta V is our key knowledge we didn't know, and the answer what we want. So we don't know the delta V. Okay, so we keep the delta V, and then we know the V1 in here. I write down in here. This is the V1, and then we know the EV. We know the EV. So we reorganize the equation 1. Delta V is equal to minus delta P divided the EV and then multiply the V1. Okay, so the delta P, the number here, so the minus 898,700 divided the EV is in here 2.2 and 1 giga. Okay, and then multiply the 10 minus 3. So you can use your calculator to compute the answers. 2.2 and divided 10 minus 3 powers, multiply the 10 minus 3 powers, and divided the 9 powers. So the answers in here is around the 4.085 10 10 minus 7 powers. And the unit, because it's a volumes, so it's a meter cubic, and we have additional minus here because the volume becomes smaller after you do the compressions. Okay, so this is our final answers. And you see the unit showing here is 10 minus 7. 10 minus 7 is quite smaller. So only for the 1 liter water, you do the compressions, but the volume change is quite smaller, like the number showing here. That indicates for the liquid water difficult to compressions. The volumes cannot be changed a lot, right? OK， 那我每学期都会这样讲，就是之前我有出过类似的这个题目，然后有一个学生他没有做计算，他就直接写说水是不可压缩的，那一个计算都没写，那我要不要给他分数？要啊，我给他100分啊，因为算出来你可以说接近于0嘛，但是他没有算，他也可以说他接近于0。不过我考试的时候你们千万不要给，因为我已经先讲不行嘛。这样你们5分钟就写好就下课了。Okay, so the idea is something like that, but you can compute by yourself, and then the answers is quite smaller. So you can say the fluid water is incompressible flow. Okay. 就是你可以先算了，然后你才去下这个定论。那你不可以说老师说，所以它不可压缩。Okay, so we still have time, so we move to the next. So as I mentioned, now we already teach the 8 fluid property already, and the final 2 is the vapor pressures and the surface tensions. I will teach in the next class. Okay, so right now I move to the stress. So for this case, we only have the 2 stress. One is the pressure stress. Another is the shear stress. Okay, and usually we call that the pressures. The pressures is related to the normal stress. So in the fluid mechanics, we tell you the normal stress is equal to the weight of the fluid. The weight of the fluid is the pressures. Okay, it's a normal stress. We call that is a pressure. So in our case, we didn't tell you the normal stress. We always say that is the pressure. That is the pressure. And another stress is the shear stress. So in our textbook, we use the shear stress, we use the tau, and the pressure, we use the P. And we know certain definition for the stress is it's computed from the ratio between the force and the acting areas. The force acting areas. So that's the common sense, so I just skip out. And then for our fluid problem, mechanism problems, hydraulic problem, as you see, this is the bridge, and there are some water flow, and the water will erode the bridge structure, right? So for hydrology problem, usually we will use the integrations, because different area we will have a different force. So we cannot follow a simple idea, just the stress multiply the small area. So we need to have the integration problems to sum of all stress acting on the small areas. So use the integration operators. Okay, so for hydraulic, we can do some numerical simulation to understand the different bridge will have the different flow conditions. The flow condition information include the flow velocity. Okay, and as I can show some movies. So this is, we can do the simulation to understand where As you see the movie, the red color showing here, and the color bar is the flow velocities. So you conduct the numerical simulation, you can understand the flow velocity distributions around your bridge. Okay, so I just showed the video in here. My purpose is because usually we can compute the different area have a different stress, and then finally we will do the integration to sum of all the force for our problems. Okay, so and sometimes we call that the pressure. So we have normal factors. And the shear stress is we have the tension factors. Okay, so not there's a common sense, so I just go quickly. And the table showing here, we summarize all force. Totally, we have the 7 force in this class. And then the first two, you already know, the pressure force and the shear force. And for the shear force, we always say that is the viscous force. So that means the shear force will have some relationship between the viscosity, right? So we call that the viscosity force. And we have additional buoyant force, surface tension force, drag force, lift force, stress force. Okay, but today we will focus on the force in here. We will focus on the force for the shear force. And I already highlight, we call that the viscous force. So this force should be related to the viscous. Okay, so I just highlight the equation showing here. The left-hand side, this is our shear stress. Okay, and then we have the mu. Mu is our viscosity. And the viscosity mu is the dynamic viscosity. And what the V? The V is not the volume. V is the flow velocity. So if you base on these equations, usually we say the dV dy. That means the V velocity is a function of the y space. And the dV over dy is indicate the velocity gradient, right? So if we have the flow velocity functions as function of the spatial, and we can compute the gradient of the velocity, multiply the viscosity, and then we can compute the shear stress. So this is a very basic equation. We call that the viscosity equation. So it's quite important in our chapter 2. So the equation formula is quite simple. The shear stress is equal to the dynamic viscosity multiplied the velocity gradient. Okay. So and the one assumptions, we call that the no-slip conditions. So that means you see the figure showing here, this is a liquid. The inside is some liquid. And the outside, this is the water, maybe the tank. This is a tank. So the black line showing here is the interface between the tank and the liquid, right? So the no-slip condition, that means the particle point in here, there is no any relatively movement between the tank and the liquid. So there is no movement between the tank and the liquid. So I just have the movie. So you can see the movie in here. You focus on the left upper corner. There's no relative movement, right? So when the tank rotates back, and the particle will go back at the same point. Okay? If there are some relative movement, the flow cannot keep going with the tank. So that's the idea. If there are some different particle, different material, the interface, usually we assume there is no slip interface. Okay, so the material particle cannot move, have a relatively movement. Okay, so in this condition, we call that no slip conditions. Okay, so as I mentioned, this is this is the flow on a round pipe. Okay, so the flow direction is along these directions. And under these conditions, we have the flow velocity profile like the black color showing here. I highlight by the yellow. This is our velocity profile. And maybe along these directions, this is the y directions. So we know the velocity function as function of the y directions is hyperbolic, is a hypo distributions. So the different location have the different velocity gradients, right? In here, the velocity gradient is like this, and in here the velocity gradient slope like this. So the different location y have a different velocity gradient, and you will have a different shear stress, right? Because the load is keep the same material, so the load the same, but at a different location A, B, C, the velocity gradient will change. So you can see this cartoon figure showing here. In the top, here the top, the velocity gradient is 0 at this point. That means the shear stress is 0, right? Because the shear stress is equal to the load and the dV dy, the velocity gradient. So at this point, the gradient is equal to 0. So we don't have any shear stress in the center line, along the center line. But on the boundary here, the round boundary here, the velocity gradient is larger. That indicates at this point, the shear stress is larger. Okay, the shear stress is larger, the velocity on this point is smaller. The shear stress is smaller, the velocity at this point will be larger. Because I tell you the shear stress is indicated the friction force. Is related to the friction force. So the friction larger, that means it's difficult to flow. So we don't have any larger flow velocity at this point. But the shear stress is smaller, so that means in that point, the material easy to flow. So you will have the higher velocity. Okay, so the smaller shear stress will have the higher flow velocity. Okay, so we just do one exercise and figure out how can we compute the shear stress. Then this is our final example today. So okay, we take a look. So please apply the viscosity equations and to calculate the shear stress in polysular flow. The flow, the water flow in the pipe, we call that is the polysular flow. OK， 水在管子里面流的这种流况，然后如果又是laminar flow, we call that is the polysular flow. The more detail can be found on the chapter 10, but not teach today. So the question is please find the shear stress at the center of the pipe. This is the one, and please find out the shear stress at the wall. So this is the 2. And the 3, please find the shear stress where R is equal to 1 centimeters. And our condition is the water is 15 degrees and the pipe diameter is 4 centimeters. Okay, so first the condition is the 15 degrees. So we, based on the table showing here, we actually know the mu values for our problems. So we can check from the tables, the mu showing here, right? Dynamic viscosity is equal to 1.14 multiplied 10 minus 3 powers, and the unit is a Newton seconds per meter square. Okay, so under the seconds, we actually know the diameter of the pipe is the 4 centimeters. That indicates 0.04 meter, right? So what are the R? As you see the coordinate in here, the center line, the R is 0. So the R maxima, I mean the maxima R, the R is radius of the pipe. So it's half of the diameter, right? So in here is 0.02 meter is the radius of the pipe. Okay, so but the question is focused on the shear stress. So the key knowledge here is how can we compute the shear stress? It's based on the viscosity equations. Mu dV here should be dr, right? Because our velocity is as a function of the radius. So this is a Vr. The function velocity is as a function of the radius. So dr. And the questions already provide the velocity in here. So for first, we should compute the dV dr. And we know the V function is the V0 minus the V0 R divided R0 square. Okay, and then we can take the differential for these functions. Sorry, I multiplied dr. And based on your calculus knowledge, so you can finish it by yourself. So I computed the minus and 2 V0 R divided R0 and multiply the R0 over 1. And so dV dr, I reorganize the number in here is minus 2 V0 and R0 square dot multiply R, right? Okay, so we still need the V0. What is the V0? It's the velocity of the flow, and showing here. So we have the velocity of the flow. The V0 is the 1 meter per second. So we can put the number for this equation inside. And so the minus 2 multiply the 1 meter per second and divided the 0.02 square and multiply R. So by use your computer, the 2 divided to 0.02 square. So this is around the minus 5,000 R. Okay? So we know the velocity gradient, so the tau is equal to the mu multiplied the dV dr. And we have the mu number is the 1.14 and 10 minus 3 powers multiply the minus 5,000 and R. So use your calculator to compute the number. It's around the 5.7 R. Okay, So go back to our questions. We need to compute the 3 answers at the different location. So first, the one is the center of the pipe. The locations is at the center of the pipe. So we know that in that case, R is equal to 0, right? Because the center, the R is 0. Okay, so we put the R equal to 0 for these equations. We have the relationship equation in here. So the tau at the center is equal to 0. Okay? So that means at the center line, the flow velocity is maxima at the center line because there is no any shear stress. So the material can flow free. Okay? And then the seconds, the locations at the wall. So the location at the wall, that means the R is equal to 0.02 meters. And then you can put the reactions, so you can compute the tau for this number is 0.02. So the tau is equal to 0.114, and the unit is Newton per meter square. And the final, the 3 is the R is equal to 0.01. You can compute it by yourself. So the answer is quite simple in here. Okay? So the basic idea is we have the viscosity equations, and the tau is equal to rho multiply the velocity gradient. So the different velocity gradient, you will have the different shear stress. So why the reason we can have a different velocity gradient? Because we at the location at the different space. And the different velocity profile at a different location will have a different velocity gradient. Okay, so it's a very important exercise. It's based on the velocity profile, the example provides me, and we can compute any locations shear stress. OK， 好，那今天这个是我们最后一个例题，那先关掉哈。